All right, so let's move on to lesson 5. We'll take a little bit of time to explain this. It can be a little bit confusing, but I threw a chart at the end for you guys that will hopefully help. So we are going to talk about Le Chatelier's principle. Nice French guy. There's a lot of French guys in chemistry. So we said a system's at equilibrium. If you remember from biology, whether it was a year ago or 2 years ago, you remember homeostasis. We want to reach homeostasis. We want to reach that balance, right? So systems, remember a system is a reaction. A system wants to be at equilibrium, but sometimes stresses are placed upon that system, and we need to know how it's going to react, and that's where Le Chatelier's principle comes in. So a stress is any change in temperature, concentration, or pressure upon a system, and then we're going to look at how that system will react. So what's going to happen to the products or the reactants in order for it to reach equilibrium. So remember that stresses are changes. So we're either adding or taking something away, or we're increasing or decreasing something. So the first stress we're going to look at is pressure. Remember, pressure, gases only, all right? This does not affect liquids or solids or aqueous equations. I'm going to put my double arrow in here because, again, the symbols didn't carry over. So when we increase the pressure, we're going to move to the side of the equation that has the least amount of moles, right? And we're going to calculate the number of moles. You don't actually have to calculate. You're going to count the coefficients. So in our example here, our reactant side, we have 3 moles of hydrogen gas and 1 mole of nitrogen gas, so we have 4 moles of gases. And on our product side, we have 2 moles of ammonia, so we have 2 moles here. So if I were to increase the pressure of this system, the shift would move in the forward direction, right? Because we're going from 4 moles here to 2 moles here. So what's now going to happen, we're now shifting, we're trying to reach equilibrium. What's going to happen is we're going to see a decrease in nitrogen, a decrease in hydrogen, and now an increase in ammonia production, right? So it's shifting over. So we're now forming more ammonia. But if we were to decrease the pressure, we're going to shift in the reverse direction. We're going to go towards where there's more moles. So we're now going to see I slid up and my little home screen came up. So we're now going to increase the nitrogen, increase the hydrogen, and decrease ammonia. Because what's happening now is this ammonia is now breaking down into its nitrogen and hydrogen to reach that equilibrium. Right? So pressure, gases only, increase, shift to less moles, decrease, shift to more moles. Right? So our next stress, temperature. So we're going to look at temperature and we're going to treat it like a product or a reactant, right? So our temperature is our heat, product, or reactant, right? So when we have an endothermic, remember it's entering the system, enter, it's going to be a reactant. It's going to be here on the left side. Whereas an exothermic reaction, remember it's exiting, exit. Let me fix that. It's going to exit the system, right? So it's going to be a product. It's going to be on the right side of the equation. Love how my arrow worked on the bottom. Okay, so when we're increasing the temperature, so we're adding more heat, so we're adding more product, it's going to favor the endothermic direction. So increase endo, and we're going to produce more product. Decrease exo. So let's look at this example below. So we have ammonia, oxygen, nitrogen monoxide, and water plus heat. So heat is a product. So this reaction, the forward direction is exothermic. I'm going to put forward here so we know which direction we're talking about. So the forward reaction is exothermic. So if I now increase the temperature, up above, I said that if increase the temperature, the endothermic reaction is favored. So our forward direction is exothermic. That means our reverse reaction is endothermic. So if I'm now increasing my temperature, I'm sending that reaction in the reverse direction, and I'm now going to increase ammonia production, increase oxygen, decrease nitrogen monoxide, and decrease water, right? Because I added heat to the system. So I favored the endothermic direction. Whereas if I decreased temperature, I would favor the forward direction, and my reactants would go down and my products would go up. So think of temperature as a reactant or a product, whether you're adding or taking away, and make sure you're aware of which direction is related to which reaction type, right? So exo or endothermic. Look at what side of the equation the heat is on and go from there. All right, and our last stress is concentration. So concentration. So it's shift that occurs when we're either adding product or reactant or taking it away. So when we're increasing the concentration, the shift is going to go in the opposite direction, right? So if we increase the concentration of ammonia, say we increase this guy, we're now going to shift in the forward direction. We're going to shift this way. So what's going to happen is oxygen is going to go down, nitrogen monoxide is going to go up, and water is going to go up, right? So we shifted away from where we at. So we added too much ammonia. So now we need to get rid of some of that by reacting with oxygen and getting our products. Whereas if we decrease the concentration of something, the shift goes towards. So decrease towards, increase away. So if we decrease the concentration of ammonia, we now need more of it to be in equilibrium. So we're going to go in that reverse direction. We're going to end up with more oxygen, and we're going to end up with less nitrogen monoxide and less water because those two are now reacting in the opposite direction to produce more ammonia. So with concentration, remember, increase, away, decrease, towards. Again, I have a nice little chart for you guys. Oh, I gotta fill in the blanks. Okay, so I will post another copy of this chart for you, but what it was on the top, it was increase concentration, shifts, opposite side. This one was increase pressure, gases only, shifts to less moles. And this one was increase temperature, shift, let's fix that so it looks a little nicer, shift in endo direction. And this last one, I didn't talk about it on its own slide. I was just going to talk about it here because it's not that it's not important, but there's really no shift. So when we add a catalyst, there is no shift. Remember, a catalyst is just speeding up the reaction, right? So speeding up reaction. So speeding up the reaction. It's not a product. It is not a reactant. So there is no shift. It's not affecting the equilibrium. It's just helping us get through the reaction faster and faster. All right, guys. Sorry, this one was a little bit longer, but I wanted to get all three of them done in one shot, so you only have 2 videos of notes to watch. Again, I will post hard copy notes of these for you guys to follow along, or if you just want to look through those. And then I'm going to make one more video after I get a drink, because my throat's a little dry, of the answer keys for the worksheets. And then I will post everything in one big chunk for you guys. And then I think I'm going to hold off on another assignment for this unit, and we're just going to do a little bit of like a review activity. I think I can do remote Kahoots or something of the sorts, and then we will do an online test probably Monday or Tuesday next week. I'll assign it, and it'll be due like a couple of days later sort of thing, and then we'll keep chugging along. So let me finish this all up for you guys, and then I'll post everything, and we will chat later.